Hello, everyone. For those of you who were waiting for the other lecture that you have in your flyers, we are very sorry. Their bodies are in Bogdan's trunk, so we've replaced them. Today, we are going to talk about the solution that we are going to present, the architectural challenges that we faced in creating a cyber range solution from scratch. As you well know, creating any sort of solution from absolute zero entails choosing different architectures and having some challenges along the way. The challenges that we are going to face in this particular solution, are the ones that we faced while creating the product. We came up with some solutions for them. Sorry, this is my first presentation. We are going to discuss a lot of moving parts, and yeah, thank you. In any big solution, we can talk about virtualized performance, concurrency issues, etc., etc. When we are talking about the cyber range, we have a lot of moving parts. In our particular implementation, there were a lot of virtual machines that needed to be spawned. There were a lot of isolated setups that needed to be deployed on the fly. And as such, we faced a lot of challenges with both the virtualization aspect and with the concurrency. Now, it all started with the actual requirement, which was to have a large number of tenants. Tenants being isolated networks where people can safely detonate all sorts of malicious payloads within a virtualized environment. Now, key point here was that the requirement was to have more than 100 tenants, each of them having a lot of virtual machines, a lot of interconnects, a lot of networks, and to keep them as isolated as possible from one another, while also allowing them, the users of the cyber range, to VPN in and use the setups as if they were directly connected. We had the following challenges. How to isolate tenant infrastructures from one another, how to ensure direct access to their respective payloads, and how to smart manage all of the resources that we had available while keeping the cost at a minimum for the higher up management. Of course, everything boils down to the storage subsystem bottlenecks, which is something that large systems, including the Amazons and the Googles of the world, are facing with when having high virtualized environments. Now, my colleague Bogdan is going to present the first two challenges, which are isolating tenant infrastructure, and he will also show you how we implemented let's say, the solution on our side.
Okay, so as my colleague was mentioning, the first problem that we had to solve was how to isolate from network point of view the infrastructures. And here what we needed to do was to be able to have multiple networks, multiple clone of that network, so for any tenant, allow those tenant access to their infrastructures, and in the same time have a safe zone, so if someone detonates a malware or anything malicious in there, it's not getting outside. Also, in most of the cases, implying same IP addresses, same network ranges deployed simultaneously. For this, we chose to create a service that runs outside of our platform, that it's acting as a virtual router forwarding instance, running on a BSD-like operating system. That allowed us to have multiple routing maps in the same time with the same subnets, allowing different users to reach with the same IP, different network. In order to control this VRF, we implemented a fully fledged REST API that allowed us to apply firewall rules on the fly, allowed us to deploy or destroy networks on the fly. And of course, allow access for VPN users, for example, to their networks. We used VPNs for differentiating between different subnets, different network layers, and these solutions allow us to scale up to 120 different tenants on a single wire, let's say. And in order to grow even more, we are scaling vertically, and we are practically deploying multiple VRF routers, basically different gateways. In order to also to communicate between hypervisor node, we are trunking all the management VLANs of the VRF routers between them. So basically, any user can access any network infrastructure at any given time. This is how it kind of looks like. These layers that you see here are basically our tenants. Each of the tenants, in our case, have up to 30 VLANs on its own. For example, different networks like kind of SCADA networks, like different military-grade networking in there, depending on the customer need. And each of the users, either connected directly to our routers or from the VPN, can access only their PCs from their layers without impacting the other users.
From a virtualization aspect, you can imagine that each tenant might have up to 7, 8, or even 10 virtual machines. When having 120 tenants in parallel on a single setup, doesn't help if you just add more hardware to the problem. The key point would be to find that equilibrium between hardware and the code changes that we are going to show you later on to extract as much power as you can from the existing setup while preserving usability, because in an isolated setup, you really need to have the users having the same experience as they were if creating a hardware cyber range and adding PCs together. So latency is at a premium there. You need to have network-like services everywhere. You need to keep latency between different VMs in the same setup at a minimum. And of course, if you want to detonate stuff and create your own setups, create your own custom setups that you can use to evaluate new exploits or tools, you need to be isolated from the rest of the network, which is what we did with the VRF router that Bogdan was telling you about. About smart resource management, obviously, there is a key point where throwing additional hardware doesn't solve any issues. So what we needed to do, or what we did, the architecture that we thought of was to actually allow each tenant space, each couple of VMs isolated by routers, IDSs within a tenant environment to reside on the same hardware node. Obviously, the entire solution means that you have to deploy a cluster on top of multiple nodes, but to keep latency at a minimum, Bogdan needed to think of a proprietary algorithm to keep every tenant space within a single physical node. Obviously, from a technical standpoint, there is a perfect possibility to allow spreading different VMs to different hardware nodes. But this comes with a cost which we weren't going to pay at this time, because physical links between servers, between nodes are expensive, and the latency makes it not really worth it. This proprietary code that Bogdan actually wrote by himself allows us to select the better alternative from all the nodes within a cluster while choosing to deploy the virtual machines of a tenant in the, let's say, node that has the most resources available. This goes to the second problem, which was how to account for RAM and vCPU provisioning while preserving usability. So we decided from an architectural standpoint not to oversubscribe RAM at any point in time, so that the virtual machines within the environment would have predictable results. What we did for certain customers is actually oversubscribe the virtual CPUs so that taking into account smaller performance, you would allow a number of tenants higher than what the setup was originally intended for. There are a lot of we call them scenarios in a library where users can single-use learn different types of attacks, different types of exploits, and those actually don't need as many resources as in a CTF, for instance. And they are not as dynamical in nature. They don't require so many resources. So then it would make sense for a small setup, even a home lab, for instance, to over-provision the physical cores that they have available to allow for spawning of more virtual machine instance.
Okay, the next problem that we needed to figure out a solution was the storage. And as you probably know, if you are working with clusters with many servers, storage is always a bottleneck, right? And it's more a problem when you want to clone, let's say, hundreds or even thousands of virtual machines in the same time, sometimes from the same source. So it's you want to read from the same source in the same time in multiple servers. For this, first of all, we had to choose our file system before going to the shared part of it. And we looked at a lot of different file system sizes with different advantages, disadvantages, like, I know, BTRF, like extended for, like ZFS, LVM. And after extensive testing, we decided to stay with ZFS because that allows us, first of all, link cloning capabilities, so snapshot, copy and write features. Allowed us deduplications of data, allowed us easy synchronizations between nodes. And on top of the ZFS, we thought about the transport layer, how we are communicating between different cluster nodes, between hypervisors. And here, first of all, we chose to take a look at iSCSI, which brings a lot of performance as opposed to, let's say, NFS or other I don't know, Samba, something like that. But we chose to use NFS for underlining transport of the file system just because NFS it's mostly available with almost any vendor of shared storage like NASes, and it's very easy to configure out of the box for customers. Choosing NFS also became with a drawback. It's less performant than iSCSI, for example, and it has also some bottlenecks. You can write or let's say read as much data at a time, much slower than iSCSI. In order to overcome this, we had to also implement some queues in our own backend, and basically from software. Limit the number of IOPS that we send to every unit in the cluster. So you will make sure we're never bottlenecking, we're never affecting the users that want to access that platform with the clones, for example. Also, another solution that we also tested, for example, distributed storage like SEPFS, and that is good, but it's good only if you have enough number of local hard drives, more than 12, let's say, per server, to have a good IO speed. We also, for more scale system, for example, like the CTF that we are holding right now at our booth, we also created a proprietary code for distributed storage using local disk, which leverages the ZFS partitions, and basically we are synchronizing over the network just the template part of the virtual machines, so they are available across all our hypervisors, so we can use link cloning on them.
The key point here is that not only a cyber range can be implemented in this manner. Any sort of virtualization that requires fast turnaround times for deployment can be used. And as you will see later in the concurrency portion, you will need to spawn a lot of VMs, means that you can't really copy hundreds of gigabytes and terabytes over the network. That's not feasible. This is why Bogdan was talking about link cloning, because the key aspect here was exactly like Amazon and Google, to spawn the environment in as few seconds as possible, because otherwise nobody wants to perform a scenario walkthrough for an hour while they have to wait an hour to get the running setup. Which brings us to the concurrency and timing aspects that we had to face, right? The idea was that the setup wasn't static in nature. We didn't pre-configure 120 tenants, spawn them 720 different VMs, and just waited for users to log in. There were, in our performance testing, there were even 700 VMs starting at once, or at least scheduled to be started as soon as possible, right? So this actually presents concurrency problems from a number of perspectives. From the hypervisor access concurrency issues, because you have to realize even in a cluster, hypervisors communicate with one another, they are syncing, they are scheduling tasks. The storage subsystem locks that Bogdan was mentioning previously, and of course, some degree of disaster mitigation and recovery. All in favor of speed, right? The speed of provisioning needs to be maximum, because you don't really want you want the advantages of a static setup, which is always on and you can connect to it, while having the advantage of also having a small setup like our NUCs next to the exit to keep the requirements, the hardware requirements, to a minimum. So
the next thing that we try to solve in our cyber range was about related to hypervisor and storage concurrency. Here, as we discussed earlier, I was saying we choose the NFS, and yeah, NFS has some problems. If you try to clone, I know, hundreds of VMs in the same time, you'll definitely have locks. In order for this to use them smoothly, we created queues based on the operations that we have. So, for example, we have some queues for cloning, some queues from destroying, and everything related to IOPS. And based on each hypervisor specifics, we allow some number of tasks that can be executed at the same time. Of course, depending on the hard drives that you have, depending on your speed and so on. So basically, we know each of our cluster node, how it can handle, how much IOP it can handle, and based on that, we are trying to queue only that it can, only the amount of tasks that it can do without going to the limits. The next thing was also about prioritization. So if you have, let's say, think of a highway, for example, where there are a lot of people trying to reach somewhere, and all the lanes are busy. It's easier to have a lane which you allow only the cars with multiple people to go first, so you can free up the highway for the others. Similar to this, we thought what are our operations which we can do, which impact many users, or at least are freeing resources. And by this, what we did was prioritizing the tasks which are freeing more resources first. So, for example, when a user wants to destroy its setup, wants to leave, we first destroy the virtual machines before trying to clone other news, because destroying leaves us space, leaves us RAM, CPU resources, and so on. We also implemented a self-adjusting timer for our service, that basically when the more users that are requesting stuff from our side, are requesting operations, the more the system will idle itself in order to have a bigger picture of what the user wants, so we can execute the tasks which are impacting more users first, instead of executing them first in, first out.
Similar to queuing, right? Because if you have If you have a bigger data set, you make more informed decisions. If you have a higher number of tasks, so a bigger idle timer, you would have to make decisions based on a bigger sample of the tasks that you are going to schedule. So you could, going back to Bogdan's analogy, the parking lot analogy, right? You want to prioritize the cars exiting the fully loaded parking lot so that others can join in and park. These are tasks that are the least time consuming with the biggest benefit in terms of speed and usability. Bogdan devised an entire algorithm, so if you want to know more about it, to get into the gory details, you can find him at the stand next to the exit and ask him directly. With regards to NFS, we had to work around some NFS inherent, let's say, limitations, right? And this was also done in code. Bogdan had to create multiple queues to overcome NFS's limitations and to prevent deadlocks in the deployment, deletion, etc., of virtual machines. For disaster scenarios, we were facing with a very complicated aspect, which was that hardware, as you have all seen yesterday at the beginning of this event, inherently fails, right? You have a cluster, you have redundancy, but what happens with the virtual machines and the guys that are actually using the cyber range? So this solution that we devised actually takes into consideration disaster recovery scenarios where if a node fails and the entire cyber range is not affected, only the machines that are present on that particular node. Even those, if you are in a CTF and you lose the node that one of the NUCs, right, that you sit on, you would be very unhappy about it. But if you use shared storage where the hard drives are not local to the NUC that you lost, you can actually have a team administrator, a range admin coming back and restarting those virtual machines environment, that tenant space, that isolated space, somewhere else on a different hardware piece. And that is very possible for shared storage, so manual recovery. On the other hand, if you have a failure in the power system and you restart the failed node, it will just add it back to the cluster and everything will be, let's say, managed by the cyber range infrastructure. The cluster, let's say, the hypervisor options, and the starting and stopping of the virtual machines. Cluster resources are monitored at all times within the cyber range solution. Now, for future challenges, there are things that we wanted to do and things that we are going to implement, such as Bogdan was describing same static setups in the sense that you have clone setups with same IPs, for instance, for the attack virtual machines, such as Kali, or for some specific servers. We want to do this more dynamic in nature so that every virtual machine has the possibility of configuring network settings, for instance. And you can do this in a lot of ways, using Ansible, using some sort of provisioning tool that's OS dependent. What we thought of was actually to reuse a VM template in an attacker or a defender scenario. This means that you would have less hard drives in your environment, right? Less things to copy, less things to duplicate. And we wanted to create a stealth VLAN-aware REST API DHCP server with IP addressing on the fly. As probably most of you know, when talking about DHCP, the bad thing about it is that once you delete the pools, or once you restart it, once you configure it, you will have the problem of either losing the existing leases, you would lose the existing clients, etc., etc. Now, we already have a piece of code that we wrote for a different project, which does exactly that. It sits in memory, it allocates the response to DHCP clients on the fly, it's REST API controllable, it can create bootp and all sorts of DHCP options to clients, and we can integrate it in our framework to spawn virtual machines with whatever network configuration we want. And also, obviously, integrating with LMS and others.
And also here, it's the DHCP server. It's VLAN aware, so that's basically the main key here. DHCP server, that's it's like a trunk responding to all the VLANs in that network in the same time, allowing even sending the same IP address in different VLANs based on the configuration, based on the scenario deployed.
Yeah, for the other project, we actually searched for this because nobody's crazy to start coding on something that exists, right? Even using existing libraries, but we found no such thing. And we needed it in this particular form, which fortunately can be quickly integrated into the cyber range to control all networking aspects. The good part is that DHCP is actually present in all operating systems and it works pretty much the same. So no more playbooks or I don't know, configuration sets or configuration items different for Windows, Linux, etc., etc. You can basically provision the whole network infrastructure just from the cyber range interface. Okay. If you want to know how this all started, I mean, this was the the smaller version of it. So the key point would be that this is the easy diagram. It just grew larger and larger with every new feature, right? So, yeah.
Since our time is up, if you have any Q&A, you can find us at the booth near the exit in the right.
Yeah. Thanks so much, but we do have time for one or two questions. I know we started a bit later today, like we're 10 minutes behind our usual schedule, but we'll catch up during the coffee break. So let's take one or two questions, and then we have one over there. Mike is coming to you. Please hold your hand up so we can see you.
Hi, thank you for the presentation. It was very interesting. Coming back to the storage, I just have one question. It's why you are choosing this type of storage instead of classical SAN, let's say, where you have block storage and you have all the features of deduplication, snapshotting, compressions on the storage side, and you just clone everything through APIs and
Yes, that's
it's just the cost an
yeah,
issue.
basically most of our customers want to stay also high cost. So we wanted a solution that implies less costs, but let's say same capabilities.
Okay, thank you.
Doesn't actually mean that we can't really deploy it on other types of storage, right?
We are actually supporting even SANs, and so we are not limited to what we implemented, but just this is the default that we are deploying with.
Mm-hmm.